So it is my pleasure to introduce Wei Fan from Berkeley, who will tell us about rational cubic fourfolds containing Veronese surfaces. So, Wei, please.
Thanks for the introduction, and thanks a lot for the chance to speak here. So I'll be talking about joint work with Kuan-Wen Lai at UMass Amherst about cubic fourfolds containing Veronese surfaces. And so I actually gave like a talk on December earlier this year at Miami. So I apologize that if you have already heard about this. Okay, so let's get started. Sorry. Okay. So yeah, so actually, like there are some backgrounds on cubic fourfolds already discussed in the talk by Professor Hassett in this conference. So I would only recall like minimum amount of background on cubic fourfolds to state our main results. Okay. And hope that's okay. So we say a cubic fourfold, the cubic hypersurface in P5 is special if its algebraic lattice, the H22 of XZ, contains a rank 2 saturated lattice that contains the square of the hyperplane class. And this rank 2 lattice K is called a labeling. Okay. And we denote the modular space is denoted by CD. So the spec is the modular space of special cubic fourfolds admitting the labeling of discriminant D. So the discriminant of this lattice equals to D. And so it's proved by Hassett that when D satisfies this numerical condition, this moduli space CD is non-empty. And moreover, it is an irreducible divisor in the moduli space of all the cubic fourfolds, okay, denoted by C. And in Professor Hassett's talk, it's also mentioned that there's some associated K3 surface when D satisfied this numerical condition. Okay. So when D satisfies this condition, it's not divisible by 4 or 9 or any prime that's modular 3 equals 2, then there exists a primitive K3 surface such that it's primitive. So there's a K3 surface such that the primitive cohomology is isomorphic to the perp of the stable. And such D is called immiscible. Okay. So there's also this kind of categorical perspective of studying cubic fourfolds. It's also mentioned a lot in this workshop conference. So this AX is the Kuznetsov component. Is the perp of this O1, O2 in the derived category of coherent sheaves on cubic fourfold. And it's proved by Kuznetsov that this category is a K3 category. Namely, the stereo functor is equivalent to shifted by 2. And this category is geometric if only if it is a special cubic fourfold with admissible discriminant. And this is proved by Edin and Thomas in the generic case and proved by this 6th author's paper in general. Okay. And it's also conjectured by Kuznetsov that cubic fourfold is rational if only if it has this associated K3 surface that it is a special cubic fourfold with admissible discriminant. And there's also related related conjecture about the relationship between the K3 category and the birational geometry of the cubic fourfolds. Namely, this conjecture by Huybrecht that if two cubic fourfolds have equivalent K3 categories, then they'll be birational to each other. Okay. And yeah, so these are some backgrounds on cubic fourfolds that I want to recall. And now I'm going to state the our main result. Okay. Yeah, sir. So feel free to interrupt me if you have any comments or questions anytime during the talk. So the first few admissible discriminants are like these 1476, 3842, and so on. And in the first four cases, it's known that they parameterize rational cubic fourfolds. And so the first part, the first main result in our paper is that there exists at least three irreducible divisors in this divisor in the homogeneous space of cubic fourfolds. So these are some like codimension 2 components in the homogeneous space of cubic fourfolds, and they parameterize rational cubic fourfolds, and they lie in these three intersections. Yeah, later we'll see like why we have the 20 here. And you can check that 20 is not admissible. That's 62, 146, and 182, they are admissible. And another result is that we proved the conjecture I just mentioned by Burbage in this special case, that when X is a very general cubic in C20, and if there's another X prime with equivalent K3 category as X, then they'll be birational to each other. Okay. Right. So that's the main result. Any questions so far? Okay. So move on to the next slide. So the main idea is that we want to find certain cubic fourfold and certain birational map from P5 to P5, the Cremona transformation, such that the image of this cubic fourfold under the Cremona transformation is still a cubic fourfold. And so suppose that we can find such pair, X and F, then if like we further assume that we start with a rational cubic fourfold, then we can use this map to produce another rational cubic fourfold. So it is like using these Cremona transformations to produce like more rational cubic fourfolds. Okay. And so we're going to consider like a particular kind of Cremona transformations that arising from Veronese surfaces in P5. Okay, so so just recall the definition of a Veronese surface. So it is given by this embedding of P2 and P5 by these quadratic monomials. Okay. And we can write down what's the defining equation of the Veronese. Okay, so suppose x0 through x5, they are the homogeneous coordinates of P5. Okay, then we can write down like the defining polynomials. So these are the defining polynomials will be like 6 quadratic polynomials given by the 2x2 minors of the symmetric matrix. Okay, so for instance, if we look at the first 2x2 minor, then we get the determinant as x0 times x2 minus x1 squared. And that, that corresponds to the fact that s squared times y squared equals to xy squared. Okay. So there's like 6 quadratic polynomials given by the determinant of this 2x2 minors. Okay. And these are the defining polynomials. So we can use these quadratic polynomials to define a birational map from P5 to P5. Right? So just use, these are the defining polynomial of the Veronese surface. Okay. And so like by definition, the base locus is going to be the Veronese because that's the common zero of these polynomials. And it's also is a result by Krogan-Katz that the inverse of this birational map if you look at the base locus, then it is again a Veronese surface. Okay, so we somehow get kind of involution of, or like given by these Cremona transformations. The Veronese, the Veronese transformations arising from the Veronese surface. Okay, and so now we have these Cremona transformations, and now we would look at the cubic fourfolds that contain a Veronese surface. Okay, and so like if we compute the intersection matrix, then we get this discriminant 20 lattice. So that's why in the result we have this C20. And just a remark that 20 is not admissible because it's divisible by 4. So there's no associated K3 for a generic cubic in C20. And they're not expected to be rational by the conjecture unless it lies in these, the intersection with some admissible locus, so some codimension 2 locus in the moduli space. Okay. So now we want to prove that, so we consider these cubic fourfolds containing Veronese, and then we want to show that under the Cremona transformation induced from the Veronese, the cubic fourfold will be mapped to another cubic fourfold, and it will contain the Veronese of, which is the base locus of the inverse. Okay, so in this way, we get some kind of an involution on the moduli space of cubic fourfolds containing Veronese. Okay, so that's the next thing we want to prove. So this is like the diagram that we're going to use in the next slide. Okay, so we have this cubic in P5, which contains the Veronese, and this Cremona transformation induced from the Veronese. And we denote the image of X by X prime. Okay, and the common, so there's a P, which is the common blowup of P5 along the Veronese on both sides. And Y is a divisor in P, which is the blowup of X along V. Okay, so we'll have this diagram. And we want to prove this proposition that I just mentioned. So the image of the cubic along through this birational transformation is another cubic containing the base locus of the inverse. Okay, and so the idea is the following. So we denote the pullback of O1 by L and pullback of O1 on P5 prime by M. So we go back to the diagram. Right. So we have these two blowups, and the L and M are classes in P. Okay. So those are the L is a pullback of O1 through this map G, and M is the pullback of O1 through this G prime. Okay. And this is L and M. Those are classes on this common blowup of P5. And E and F are exceptional classes of these two blowups. Okay. And now, because the transformation F and F inverse, they're both given by projected defining polynomials, okay, by the definition of these two maps. So so we have these two relations, right? So M equals to 2 times L minus the exceptional class, and similarly L equals to 2M minus F. So here 2 is coming from like their projected defining polynomials. Okay, and because X is a cubic, so the strict transform YP, the Y, so maybe, yeah, so that's the strict transform in inside P. So this also gives a divided class. And so it will be 3L minus E, right? Because X is a cubic. So there's a 3 here. And now, so the proposition essentially follows from this observation that 3L minus E will equals to L plus M, because M is 2L minus E. Right? So if you plug in this, we get 3M minus E. And this is kind of symmetric on both sides, so this equals to 3M minus F. Okay. So the image will also be a cubic containing the base locus. Okay, so that's the idea of the proof. Okay. Any questions so far? So this somehow gives an involution on C20, right? The moduli containing Veronese, of cubic containing Veronese. Okay. So the first part of the main theorem we kind of restated as follows. So suppose X is a general cubic in C20, and so we show that X and its image in under this Cremona transformation, they're not isomorphic cubic fourfolds, but they have equivalent K3 categories. And also X prime is this image is a unique cubic fourfolds that satisfy these two conditions. Okay, so I'm going to sketch the proof of these three statements. So what these will imply is that like this conjecture that K3 category is equivalent implies birational is true in this case. So when one of them is a general cubic in C20, because by this theorem, we know that when we have this, and like assuming one of them is this general cubic in C20, then X prime, like say X is like general cubic in C20, then X prime must be either X or X prime, right, by the theorem, because X prime is a unique cubic fourfold satisfy the second condition. So this would imply that like X and X prime are birational by our construction of X prime, because that's the image of this Cremona transformation. Okay. So now I'm going to sketch the proof of these three statements. Okay. Oh, sorry, there's another slide. So there's a more general version of the third statement. So the third statement, so we can think of the third statement as the number of cubic fourfolds with the equivalent K3 category as X is equal to 2, right? So it's either X or X prime. And so this is similar to like notion of Fourier-Mukai partners of K3 surfaces, right? That contain how many K3 surface will share the equivalent derived category. And we have a counting formula for other discriminant, as long as the discriminant is not divisible by 9. Okay, so for a general cubic in CD, where D is not divisible by 9, we also give a counting formula for this number of isomorphic classes of cubic fourfolds that satisfy that share the equivalent K3 categories. And the proof is really similar to the counting of Fourier-Mukai partner for K3 surfaces given by Aguizo and Hosono, Lian, Aguizo, Yao. So, but we're going to, like, for our theorem, we're just implying D equals to 20, and then that'll be enough. Okay. So let's first prove that X and X prime have equivalent K3 categories. So recall that X and X prime are related by this Cremona transformation. Okay. And the proof is, So these ideas, these are not some. So these are ideas that are kind of well known. Right? So to prove this, we use the derived Torelli type theorem by Hilbert. So reduce the statement to an equivalent statement about Hodge symmetry on the Mukai lattices of the K3 category. And because these two cubic fourfolds are related by certain blowups and blowdowns, and we can use the blowup formula to relate the transcendental lattice of these two cubic fourfolds. And so there will be, so you can use the blowup formula to show there is a Hodge symmetry between the transcendental lattice of these two cubic fourfolds. And then we use the uniqueness of certain lattice embedding theorem by Nicolin. So that allows us to extend the isometry on transcendental lattice to isometry on Mukai lattice, and then apply the derived Torelli, we get the equivalence of K3 categories. So that's the ingredients. So let me just briefly recall this derived the Mukai lattice and derived Torelli type theory. So we denote this Mukai lattice of AxAX to be this topological equivalent group of the category. And as an abstract lattice, it is isomorphic to a Mukai lattice of K3 surface. Okay. And there's also a Wei Hall structure induced from the Hall structure on cubic fourfold. And so there's a result by Hilbert that for a general special cubic fourfold CD, the condition that the K3 category of X is equivalent to another cubic X prime is equivalent to their Mukai lattice are Hodge symmetric. Okay, and so okay, and yeah, so this is another ingredient that I mentioned about transcendental lattice. So it's the perp of the algebraic lattice. Okay? And so we can use so we have this diagram connecting X and X prime. So these are blowups along the Veronese on in X. There's a Veronese V in X and a V prime in X prime. And so we can apply blowup formula of this cohomology blowup and have this kind of decomposition. And this will allow us to identify the Hall structure on the transcendental lattice of X and X prime through this blowup. Okay. And so now the next step is to kind of lift this isometry on the transcendental lattice to the Mukai lattice. Okay. So, right. So, okay, so there's a notion of transcendental lattice and algebraic lattice in this Mukai lattice. And I'm not going to recall the definition, but they were denoted by T and N. And there's an Hodge symmetry between this TAX of the K3 category with the transcendental lattice of X after a shift. And so we have this diagram, right? So this is what we have from the blowup formula, okay? And they can be identified with the transcendental part of the Mukai lattice. So let's denote this lattice by lambda prime and this lattice by lambda. So we think of these as abstract lattices. Okay? And we can apply a result of Nicolin that in this case, the embedding from lambda prime to lambda is unique up to an symmetry on lambda. Okay. So this will allows us to extend the Hodge symmetry on transcendental lattice to the Mukai lattice, and by Herbert's theorem that implies the K3 categories are equivalent. Okay, so that's the sketch of the proof of the equivalence of the K3 categories. Okay, so essentially just follows from the identifying the transcendental lattice and this extension result. And okay, so this is the idea for proving X and X prime are not isomorphic. Okay, so so we can use again. So we have these isometries from the blow-up formula, and we can analyze what's the action on the discriminant groups of the transcendental lattice. So like there's certain canonical identification between the discriminant group of Tx with Z20. So like it's a cyclic group of order 20. And so there's an identification between this group with Z20 and another canonical identification of discriminant of Tx prime with Z20. So we can kind of represent this map by kind of multiplication in the group Z20, and yeah, and like this map can be computed. So first we can kind of transform this map to like a map between the discriminant group of certain algebraic lattice, and then we can use some intersection theoretic computation on the algebraic lattice to understand this map on the discriminant group. And so it turns out that this map is like multiplication by 9 on the group Z20. and now assume the contrary, that X and X prime are isomorphic, then suppose that then this will induce isometry on the transcendental lattice of X prime between X and X prime. And then, so if we look at this composition, then by the first part, we can show that the action on the discriminant group is multiplication by 9. But this contradicts with the fact that the only Hodge symmetries on Tx is plus or minus identity. Okay. And yeah, so the proof of this non-isomorphism between X and X prime essentially follows from analyzing the action on the discriminant groups through these identification, and the fact that the only Hodge symmetries on Tx is plus or minus identity. And the similar argument that was used in the work of Hazard and Lai. Okay. So yeah, so this is just recalling the algebraic lattice, and they're identified. So the algebraic lattice on Y and X are related in this way. So so when X is like a general cubic, then AX will have rank 2, and this will have rank, AY will have rank 3. And these are classes on AY. And similarly, there like these are classes on arising from X prime. There are also classes on AY. And we can use some intersection theoretic computation to relate these classes with these classes, because they are all classes in AY. Okay. So the proposition, so the statement that I mentioned is this. So when X is general in a general element in C20, the isometry on the induced on the discriminant group induced from the identification of the transcendental lattice if it's given by multiplication by 9. And the proof is roughly what I just mentioned. So we can, because AY and TY form a orthogonal complement in this unimodular lattice. So we can the statement about this map between dt can be transformed into the statement about dA tilde, and we can compute this map by some intersection theoretic computations. Okay, and so to conclude the proof of the non-isomorphism, so if X and X prime were isomorphic, then they're projective equivalent, and the projective isomorphism would take it's hyperplane class to hyperplane class and V prime to V. So so in particular, like this induced map on the discriminant group of the transcendental lattice will be given by just multiplication by 1. And so now we have two Hodge symmetries between the transcendental lattice, one arising from the Cremona transformation, and the other arising from this assumed projected isomorphism. And if we compose these two together, then we get an asymmetry on the transcendental lattice whose action on the discriminant group is given by multiplication by 9. And that will contradict with this fact that when X is general cubic fourfold and this some special divisor, then the Hodge symmetries can only be plus or minus identity. Okay. Okay. So now I will sketch the last part about the counting of Fourier-Mukai partners of AX. So counting of the number of how many isomorphic classes of cubic fourfolds that share the same K3 category. So there is a lattice called A2 inside the algebraic lattice of the category AX. And so the property that we're going to use is that the perp of A2 in the Mukai lattice is isomorphic to the primitive homology of X. So by the Torelli theorem for cubic fourfolds, if the two cubic fourfolds are isomorphic if and only if their A2 perp I are Hodge symmetric. Okay. And so the strategy is the following. So it's really similar to the strategy for counting Fourier-Mukai partners for K3 surfaces by Aguizo and Hosono, then Aguizo Yao. So we fix a general cubic X in C20, okay? And we want to count the number of Fourier-Mukai partners. And so we define like T to be the transcendental lattice, okay, and S to be this intersection. And it turns out it's a rank 1 lattice where L squared is self-intersection is -60. So the analog of these two lattices in the counting of the K3 case is this is a transcendental lattice, and this is analog to the neurons of free of a K3 surface. So if we fix X, then we can fix these two lattices where T has a Wei Hodge structure. Okay. And so we denote, so given X, so then we induce this T and S, then we denote the set of even lattices L to be the following. So L should be in between S plus T and S dual plus T dual. And then this L satisfied the other two conditions. So, so this lattice L, if it satisfies these conditions, it also has a Wei 2 hot structure induced from T. So what we'll see later is that for any Fourier-Mukai partner of X, so another cubic with the same K3 category, any such cubic fourfold will induce exactly two elements in MST. Okay, so and this assignment is not overlapped, so there cannot be two cubic fourfolds assigning the same elements in MST. So there's a 2-to-1 correspondence between the Fourier-Mukai partners and the lattices in MST. So the counting problem of Fourier-Mukai partner just reduces to the counting of the number of such lattices. Okay. So that's what we're going to do. And so we can show that if Y is the Fourier-Mukai partner, then there exists an asymmetry between this is the S of X, we replace this Y by X. So there exists a symmetry between S and Sy, and a symmetry between T and Ty. So these two isometries will induce this isometry between this duo of S plus duo of T of Y to this duo of S plus duo of T of X. And so if we have this isometry, then we can look at the image of the A2 perp of Y. Okay, and the claim is that this image of A2 Y perp will be a lattice that satisfies the condition of it would be an element in MST. Okay, so yeah, so the point is that for any Fourier-Mukai partner Y and any such isometry F and G, this triple will induce an element in MST. Okay, and we can show that the only isometries from S to Sy and Ty are given by plus or minus F and plus or minus G. So there's only two possible isometries here and only two possible isometries here. And this just follows, this is a rank 1 lattice, so it's kind of clear. And this follows from the fact that the transcendental lattice only has, the only isometries are plus or minus identity. Okay. So for any cubic, so for any Fourier-Mukai partner is cubic Y, there's only two possibilities for this isometry and two possibilities for this isometry. And you can show that if we have the same Fourier-Mukai partner and we check, look at these 4 possible combinations, then 2 of them will give the same element in MST. Okay. So yeah, so every Fourier-Mukai partner will induce 2 elements in MST. And also this assignment cannot overlap because they are the image of this A2Y perp. So if there were 2 Fourier-Mukai partners like Y and Y prime that give the same elements in MST, and that would imply that A2Y perp and A2Y prime perp are isometric. Then by Torelli theorem, that implies Y and Y prime are isomorphic. Okay. So yeah, so this assignment, this 2-to-1 assignment cannot overlap. So in other words, the Fourier-Mukai partner, the number of Fourier-Mukai partner is equals to 1/2 of the number of such lattices in this set MST. And then it's a fairly easy calculation to compute the number of such over lattices, and it's 4. So this shows that the number of Fourier-Mukai partner of a general element in C20 is equal to 2. Okay. So yeah, so it's only like X and X prime, and X prime is the image of the Cremona transformation. Okay, so that's the yeah, that's a sketch of the proof. Okay. Yeah, sorry, I think I'm going a bit too fast, but is there any questions so far? Okay, yeah, I think I'm going to end like pretty soon. Sorry about this. So I only have two slides left. So now I want to talk about the like these like new sort of new rational cubic fourfolds arising from these Cremona transformations. So the idea is that for instance, so we start with some intersection where we know they parameterize rational cubic fourfolds, right? So we know C38 parameterize rational cubic fourfolds. And so like this intersection is going to have like several irreducible components, and we pick one of them. Okay, so yeah, so here you can see like the discriminant of h squared and t is 38. So the 2x2 minor of the first and third columns and rows. And 236 here denotes the determinant of this 3x3 matrix. And so for a cubic in this irreducible component, we can apply the Cremona transformation that we just mentioned. And it turns out that this would give like another cubic fourfold with the algebraic lattice with the intersection of the algebraic lattice looks like this. So here we still have a Veronese, right, V prime, and there's an extra class T prime. And so you can check that this lattice is equivalent to this intersection matrix. And if we look at, again, the first and third rows and columns, then we can see this is a labeling with discriminant 62. And one can check that this doesn't, like, there's no rank 2 sublattice with labeling with discriminant like equals to 14 or 26 or 38, 42. And so, yeah, so we can use the Cremona transformations to produce some new rational cubic fourfolds. And the same argument works for like other like C26 and 42. And but somehow doesn't work for C14. So for C14, you can check that all the irreducible components, if we apply this Cremona transformation, then they will just stay, like they will be like one of these 14 or 26 or 38, 42. So they won't produce like new rational cubic fourfolds. But yeah, for 26, 32, 48, we can actually get something that's not in this list. Okay. Yeah, so I think that's all I have today. Yeah, I'm sorry that I'm going perhaps too fast, but thanks a lot for your attention. Okay, yeah, stop here.
Let's thank you, Wei. Are there any questions? Okay, then let's thank you again. And we will resume at 3:30 Eastern time. Thank you, everybody.